Now, theoretically, you have already downloaded your slides and printed them. So as we go through this presentation, you can be taking notes on it, or you reviewed a video of chapter of alkanes and took notes on it, and you're going to be refining those notes as we go through this today. Okay, so the first group of organic compounds we're going to talk about are alkanes. They are the simplest, and basically there are single bonds only, no double bonds, and they're only carbon-carbon and carbon-hydrogen bonds only. They're also very, very ubiquitous. We use them for fuels. They're just all over the place. Um, we also use them as a base for making other organic compounds. Now, normally people talk about organic chemistry is the study of carbon. Um, the thing is, it's more than that. It's really the study of carbon and oxygen and nitrogen and sulfur and phosphorus, mostly compounds. Um, Inorganic chemistry is more of a focus on the elements themselves as opposed to the combinations you get in organic and biochemistry. Okay, there are a whole bunch of organic compounds compared to inorganic compounds. Um, when you compare the two, organic compounds are usually covalent, but there are exceptions. For example, acids, organic acids. Inorganic compounds are usually ionic. The bonds forces are usually weak. With inorganic compounds, they're very strong. For example, to melt an ionic compound or inorganic compound, it takes a lot of energy to break it up, where organic compounds melt pretty low temperature. Flammability, frequently organic compounds are flammable. You can burn them. Inorganic, usually you can't. Um, Soluble in water is often low, exceptions to that when they say often. And then inorganic compounds are often high. Organic compounds frequently are non-conductors, where inorganic compounds are, which is mostly because they're ionic. And then the rate of chemical reactions is usually slow with organic, but there's a lot of exceptions to that. For example, combustion goes quite fast. Um, and then inorganic compounds, the reactions go fast. I mean, that's just a general comparison between the two. Okay, carbon can bond to itself and carbon can bond to other atoms. Those include oxygen, nitrogen, phosphorus, sulfur, silicone, just on and on and on. The Now there's two kinds of models we're going to be using. I talked about this Monday a little bit, and for line drawings, we're not going to be using either one of these. The only two we're going to be using are the formulas. For example, that. But most of the time, organic chemists use line drawing versions. So, for example, if we were looking at C3H 8. This would be what it looks like. Okay, so as you remember from Monday, at the beginning of a line drawing is a carbon, at the end is a carbon, and anytime there's a kink, there's a carbon. So we're going to go carbon beginning, carbon end, carbon kink. And then we need the associated number of hydrogens. So this is 3 here, 3 here, 2 there. Now remember, carbon has 4 bonds. So we have carbon-carbons 1 plus 3 is 4. Same on this end. Up here we've got, that's a 2 there. Up here in the middle on the kink, we've got 2 carbon-carbon bonds. That leaves 2 hydrogens left over. Hence there's 8 hydrogens. Okay, so that's what's built in to that. This here. So whenever we draw stuff, it's going to be in the line format. Now, and most of the time, textbooks use line drawings. Our textbook, for example, uses line drawings. The slides I obtained don't use line drawings, so I modified it to include line drawings. It's a good set of slides, though. I've been using these for quite a long time. Now, there's another concept called an isomer. And in 305, you learned about an isomer being differing in the number of neutrons, like C12, C14. C14 has 2 more neutrons than C12. However, in organic chemistry, there's a lot of different kinds of isomers. Organic isomers have identical molecular formulas. For example, the formula for both of these compounds is C2H6O. But you can draw 2 Lewis structures that are legal. Now, this is what they look like from a line drawing. Okay, so we've got carbon, 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 carbon. 2 carbons, 2 carbons. And then 3, 2, 1, 6 hydrogens altogether, or 3 and 3. This is an alcohol because it's got an OH. This is an ether because it's got a COC here. And this is a COH. Now this is, we're going to get into those in immense detail when we talk about alcohols. Okay, now hanging off of the carbons are something called functional groups. Those functional groups determine the chemical characteristics of that organic molecule. This is an alcohol, this is an aldehyde, this is an ether. This is unit 2, this is unit 1, unit 1. Now, and it says, except for alkanes, it isn't just alkanes, it's alkenes and alkynes. All 3 of those contain, the functional group is H, which is weird because it's almost like a non-functional group. So alkanes are, because they're so simple, a lot of things are kind of almost like exceptions. You'll see that when we get into the unit 2. Okay, these are the three kinds of depictions of our molecules. Um, we're not going to be using this for sure. With all the C's and the H's, we're going to be using this instead. Now, to draw a formula for this, we're going to have 1, 2, 3, 4 carbons. And we've got 3 here, 2 here, 2 here, 3 here. So that is 6 plus 4 is 10. Would be the formula for that structure there. Now, your dry lab 1 is really a number of worksheets that include alkanes, but they also include alcohol and other things. So when we get into that, I'm going to explain how to do that. It's a pretty long, you're going to get 20 points for it also. But it's a pretty long series of worksheets, and it's works quite well. Okay, now let me explain the difference between, there are 3 kinds of hydrocarbons. Now, hydrocarbons is a very generic term that says, I want a molecule with only carbon and only hydrogen in it. But there are different versions of hydrocarbons. There are alkanes, alkenes, and alkynes. So this is single. This is single plus double. This is single plus double plus triple. Now, there are no alkynes natively in the biological system, so we are not going to touch upon that because this is an allied health strand. So we're only going to be working with alkanes and alkenes. Also, there's something called aromatics that are also called hydrocarbons, and the aromatics contain benzene. And benzene, I'm going to talk about, is a little later today. Benzene is a 6 carbon, that's a B. Benzene is a 6 carbon hydrocarbon. And there's something called resonance. And that's what that 0 is in the middle. Okay, and there's a little subsection on that. I'll talk at more length about what that means. Okay, so here are the 4 classes. This is what a triple bond looks like. Now, of the 3 alkanes, alkenes, and alkynes, there are 2 groups. One's called saturated, meaning that single bonded to single bonded carbons, and then carbon-hydrogen single bonds. And there are no more available spaces for hydrogens. Alkenes have a double bond in there, and that takes up 2 of the hydrogens. So they call that unsaturated. That includes this is what benzene looks like, and there needs to be, this is the other way to write benzene, with a single, double, single, double, single, double, alternating single, double bond. The shorthand way of writing it is just putting a 0 in the middle of it. Okay, so you've heard of unsaturated fats, for example. That means the unsaturated fats have double bonds in them. Saturated fats don't. Saturated fats are the official unhealthy fats, and some unsaturated fats are considered healthy. For example, olive oil is considered a healthy fat, and the ones that are healthy have only one double bond. The other ones have multiple double bonds. That's why they call them polyunsaturated. So, so unsaturated, we're talking about one double bond. Polyunsaturated, we are talking about two or more double bonds. Okay. Now alkanes, the simplest one would be one carbon, and that means that's CH4, and that's called methane. And then when we start adding carbons, we have a corresponding set of hydrogens that go with it. So the deal is so if you have, for example, three carbons, the number of hydrogen is 2 times 3 plus 2. So that would be 8. So these can get quite large. I mean, we're talking 30, 40 carbons long. For example, diesel's 23 carbons long. Generally, gasoline is 8 carbons long. Asphalt can be a couple hundred carbons long, so it really varies. Okay, then within the alkanes, there are two kinds of carbon organizations. One is a straight chain, and the other is a branch chain. Okay, so straight chain is just a string of carbons. Branched means that we have, if we're looking at a carbon backbone here, we have carbons that are on either side of that. And we're going to get into this. There's different kinds of branching. I'm going to get into that in more detail in a few minutes here. Okay, so if we were to look at this, guy here, it's going to look like this. N means normal. That means straight chain. Here, iso is a type of branch. So butane is 4 carbons. However, if it says N, we know they're all straight chain. If there's something else other than N there, we still have 4 carbons, but the organization is going to be not straight. So if there's anything here, a prefix, that means non-straight. Okay, so a lot of this will come into play and make more sense as we start to put these together. So it's kind of cryptic right now. Now, another thing about single carbon-carbon bonds is they are free to rotate. So for example, we've got, let's clean this up here. Okay, so we've got 4 carbons, but you can see the structures look different. But they're not really different. They look different is because this single carbon-carbon bond can freely rotate, spin around. Now, if you have a cyclic alkane, or a ring alkane, they do not freely spin. Okay, these are rigid. Okay, now that's important to note. I'm going to show you in a little while here why this is a big deal. So non-cyclic alkanes can move fairly easily by their carbon-carbon spinning. But as soon as we get into a ring or cyclic version of that alkane, that's no longer true. The thing becomes rigid. Now, there's a concept called steric hindrance. Hindrance means that something is harder to do. So what happens up here, we've got the situation where this carbon on the right can spin. And that means there's different versions. If you were to take a snapshot of that in real time, it would look different. However, one of those versions is more stable than the other. And that has to do with this concept of steric hindrance. In this situation, we have the methyl groups close together. Here, the methyl groups are farther apart. So let's call this A. So the steric hindrance on A is higher than the steric hindrance on B, because in B, the methyl groups up here are farther apart. So the steric hindrance comes into play from a stability standpoint. So if we're looking at stability, let's do it over here. B is more stable than A. B has less steric hindrance than A. Now, stability is going to rule the roost in this class. You're going to be looking at situations where we're going to undergo a reaction. And the reaction is going to produce multiple products. And the question is which is more stable? The one that's most stable is the one that's has more of, because it's more stable. Now, we're going to see when we make aspirin in a few weeks that we're going to end up with aspirin itself as one product, but we're also going to have some other things. So the deal is whenever you make something, you want to minimize the side products and maximize the thing you're aim to synthesize. That's less waste that way. You get more product if the product is more stable than the non-products. Okay, bottom line in all this is I need to turn that off. How can I turn that off? Um, we're going to see that when we get into reactions here. Okay. Um, so this is kind of the same thing here. We've got this carbon and that carbon, and that single bond is freely rotating. So when it rotates up where the methyl groups are sorted together, that's the least stable. The most stable is when this methyl group is farthest away from this methyl group. Okay, when we get into organic chemistry, we need to talk about something called a carbon backbone. And what a carbon backbone is, it is the longest chain of unbranched carbons. So what I like to do is add a highlighter to highlight the carbon backbone. And I want to use the top two as examples. So we're going to take our yellow marker, and we're going to find the longest chain of carbons. Okay, so let's look at the one on the left. Okay, so we go, there's 1, 2, 3, 4, 5 carbons. So that's pentane. Now notice my marker did not leave the paper. To cover all the carbons. So that's the longest backbone. And it appears like they're different molecules. But these two upper molecules are the same molecule only because these guys can freely rotate. Every single one. So it changes the look of it. But because we took the marker and went along and covered every carbon and we didn't have to lift it, we know that that's the backbone. Okay, this backbone has got 1, 2, 3, 4, 5 carbons in it. 1, 2, 3, 4, 5. Now I want to contrast that to the molecules below. All right, so we're going to take our highlighter now, start here. Up, we missed a carbon. That means that this backbone is branched because there is a carbon off the backbone. Now we can do this two different ways. If we start on the top carbon, we can go that way. We still haven't covered all the carbons. That's the deal. You got to cover all the carbons like we did up here without raising your pen. Okay, let's go to the one on the right. Say we start up here in the top right. I still haven't covered all the carbons, so this is branched again. And they call that branching off the backbone. Now, frequently you'll have two ways, or even 3 or 4 ways, to figure out the backbone. and you pick the backbone that's the longest. And I'm going to add a caveat here that doesn't apply to alkanes, but it applies to everything else. The backbone has to contain the functional group. And that's not stressed in this alkanes, but it's stressed heavily on everything else. So and that could be the functional group, could be a double bond, it could be a OH group, it could be an NO2 group, it could be a whole host of things. Now, in the alkanes chapter, we don't differentiate the functional group because it's an H, which kind of blends into all the other H's. So when we get to alkenes, the next functional group we're going to be talking about, the backbone has, no exceptions, has to include the functional group. Okay, and since these are straight chain, these are both considered normal. So if you have a carbon off the backbone, it's then branched. And depending on how complex the molecule is, the branching can be quite extensive. Okay, we also have to number the carbons on the backbone. So there's usually two ways to do this. If we start from the left and count, start from the right and count. For example, on this guy here. Now we're counting the carbons on the backbone, not the branch carbons. Okay, so the yellow here is the backbone. So we can start from the left or the right. Now, which is correct? Which is correct? Okay, the way to determine that is if you have a branch, we have to name the carbon the branch is coming off of when we start to name this stuff. So we're going to name this carbon here as the carbon that the branch is coming off of. Well, it depends on which way you number it. We've got two options. It can be carbon 2 or carbon 3. And because 2 is smaller than 3, the red is the proper numbering of the backbone. But you start going both ways and look at. Now, if there's no branching, it doesn't matter which one you use. But if there is branching, then you have to figure out which end gives you the lowest number carbon on the branching. Same with this one here. Okay, so we've got 1, 2, 3, 4, or 1, 2, 3, 4. Notice the branching is on this carbon here. Okay, so it can either be carbon 2 or carbon 3. So we're going to use carbon, the blue numbering on this one here. So the red goes away. Okay, now this is really important. This and this. And there's two parts to this. The part on the right is when we get into branching. So this is This is for backbone. And this would be for branching. Same down here. Now, you need to know this. This you can have a chart already, notes card, but this you cannot have on your notes card, the upper one. Hence the little stars. Another point is whenever you do your termination here, the branch carbons, the number of branch carbons on any particular branch cannot be longer than the backbone. If that's so, then you've not identified the backbone properly. The backbone's got to be the longest one. Branches are all shorter than the backbone. Okay. So let me show you some examples of how these come into play. Let's say we've got that molecule. Now, we have, first thing we do is we identify the backbone. The next thing we do is to figure out numbering, because we have a branch here. This methyl group here is off the backbone. It's not part of the backbone. So what we're going to do is we need to figure the numbering. So if I start from the right, the number is going to go 1, 2, 3, 4. If I start from the left, it's going to go 1, 2, 3. So 2 is smaller than, so we start numbering from the right. How many carbons is on the backbone? 1, 2, 3, 4. Okay, so that's going to be butane, 4 carbons. Okay, but we're not done yet though, because we have a branch. The branch is 1 carbon long, so that's a methyl branch. And what carbon is it on? It's on carbon number 2, butane. Okay, so this identifies the backbone. And this is the branch. So this is how to use these charts. Now these charts are going to be really important. You're going to be using them all the time when we start naming organic compounds. Okay, you can also have non-carbon, that's what this means. Alkyl is carbon. So non-alkyl would be non-carbon. Like fluorine, chlorine, bromine, iodine, nitrate, amino, OH. There's a number of them. And those are going to be treated like a branch. So you've got a number, you got to figure out what carbon number that non-acyl branch is coming off of. For example, in this 3 carbon molecule like this, the backbone is 1, 2, 3 carbons. So it's going to be a propane. And we have carbon number 2 is where the chlorine is coming off. That's 2-chloropropane.
Professor, we had a question in the comments about how to know uh, if we should count the carbon backbone from the left or right, or which side. How do we determine that?
On this chart here,
Yeah.
okay, that's going to be the yellow backbone that you do before you do any naming at all. You have the structure, you have to identify where's the main backbone, carbon backbone. And then we look at, are there any carbons off the backbone? So the backbone is named via these guys here. And then the branches are named via these guys. So did that answer your question? I'm not looking at the,
Well, let's say for the highlighted thing that you drew on the right,
yeah,
with the where you counted from the right instead of the left, can you explain why it's numbered that way instead of one from the left?
yeah. Okay, so tell me blue or red numbers gives me a lower number, the carbon for that methyl branch. This here's the carbon where that methyl group is coming off of. Which is lower, 3 or 2?
Oh, I see. So from the left side, there's the two kinks. So the first carbon on the left, first kink, that's a second carbon, third kink, that's a third carbon, and the methyl group comes off of that. So there's three carbons there.
Yeah.
And if you count from the right, there's the first carbon on the right, one kink being the second carbon, the methyl comes off of there. Because there's only two on the right side before that methyl group comes off, that's where you start from.
Yeah, exactly.
Got it.
So you count both ways, and then you look at where your branches are. If there's just one branch, it's simple, but you can have multiple branches. And you just look at the carbons, and you look at the lowest carbon number is going to be the correct way to number the backbone. Now you can do in different colors. I like to use lots of different colors when I'm doing organic chemistry. You're gonna have functional group colors, you're gonna have backbone colors, and branch colors. And I use the branch as non-color. Okay, did that numbering make sense? That was Connor, right?
Yeah. I think some more examples as we keep going might help, but I think I understand it so far.
Yeah, we're gonna do, and the dry lab one practices this a lot as well. So you can practice once you start in the dry lab. Okay,
Professor,
I-
you said that we're doing these in dry lab today.
no, now the dry lab today for you guys, Wednesday people, is dry
Hmm.
lab 0, which
Okay,
is doing Lewis dot structures.
got it. Okay, thank you.
Yeah, this is dry lab 1 starts next week.
Perfect. Thanks.
Okay, so let's talk about the official naming of alkanes. Now, there are 2 ways to name. There's the common name and the IUPAC name. IUPAC is the international standard for naming organic compounds. There's an IUPAC way for naming enzymes. There's an IUPAC way of naming biochemical compounds. Biochemical compounds tend to be extremely complicated to name. That's why they usually use the common name. Unfortunately, the common names differ sometimes from country to country. Like for example, water. The IUPAC name for water is dihydrogen monoxide. Now, or water, common name. Let's go to Mexico. Water is not named water. It's aqua. But the IUPAC name is the same. So we're going to be using both here, mostly the IUPAC name, except when we get into biochemistry, then we're using the common name. All right, so every name has got three parts. The first part is optional because that has to do with branching. If you have no branching, you have no prefix. This is the longest carbon chain. So this is going to be, for my examples, is highlighted in yellow. The functional group I highlight in blue. And I need a blue highlighter. And then the branching I leave as uncolored. Okay. So the prefix has got the number, like you can have two methyls or three methyls, and what kind of group is it? Is it methyl, ethyl, whatever? Okay. So there's two parts to the prefix. The longest chain in yellow is going to be just numbers. 1 through, let me give an example of a wild one. Who knows what THA is? Who's health conscious in this class? If you're health conscious at all, you will begin to appreciate DHA. There's one that goes along with it. It's called EPA. These are omega-3 fatty acids. Is doca hexenoic acid. This is cosa pentaenoic acid. Those are common names. And you're going to be learning the IUPAC name for those as well. So these are so long, they abbreviate them. But these, for example, if you take krill pills, they're loaded with these guys. But when you buy omega-3 fatty acids, usually they will list on the container how much of these you got in milligrams. But anyway, the biochemical side of this class, we're going to be using common names. The organic side, we're going to be using IUPAC names 99% of the time. Okay, so you need to know these prefixes. Now, in the past, you've learned one is uno, two is di, or not, excuse me, not uno, mono. So there's mono, di, tri, tetra, penta. Okay, in organic chemistry, they don't name them that way. This is meth, eth, prop, bu, and then penta, hex, hepta, octa, nona, deca. And this just refers to the number of the prefix. So if you've got two methyls, it'll be dimethyl. So the numbers go mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, so that's you have to worry about this if you have branches. If you don't have any branches, you don't have to worry about that. As far as the backbone, you just need to count. And that'll determine then here which one of these you're going to be using. So this is backbone stuff. Okay, and then lastly on the ending, there is a name for each functional group. Okay, so okay, for alkanes, it's going to be ANE. For alkenes, it's going to be ENE. It kind of look like that part. For alcohols, it's going to be OL. And then for benzene or aromatics, it's going to be based on benzene. Okay. And one thing about the branching, um,
Can you go back to the alcohol list?
which one?
To the one you were just writing.
This one?
The one in the right side, please.
This here?
Yes, thank you.
Okay. Now for this subunit on alkanes, so we're just going to work. This will be the functional group name ANE, like propane. Okay, functional group ANE. That means it's an alkane. Propa, 3 carbons long. So propane is a 3-carbon alkane. No branching. All right, so let's do a formal process now on naming. Okay, so we've got this guy here. Let's, okay, first thing we need to do is identify the backbone. Now the backbone is going to be this long string of carbons. Okay, and how do we number it? Now it already numbered it for you, but you don't know that yet. So we have to do it 2 different ways. So I'm going to start over here and count 1, 2, 3, 4, 5. We start on the right, we count 1, 2, 3, 4, 5 in black. Okay, so the branch is on the second carbon on the right side. So the numbering system is the one in black because it's carbon 2 rather than blue carbon number 4. So we're not going to use the blue. So in fact, let's this in yellow. Okay, so how do we name this thing? 3 parts. Okay, it's 3 parts because we have a branch. If we had no branch here, then we only have 2 parts. Okay, first thing we need to do is name the backbone. How many carbons are in the backbone? 5. 5 carbons in the backbone. So that's going to be a penta. What kind of functional group is it? Well, they're all H's, so it's going to be an alkane or an ANE. So this is pentane. And then because it has a branch, what is number 1? What's the carbon number on the backbone that the branch occurs? And how long is it? And how many are there? Now, we can name this 2-methylpentane. This means carbon branch appears in carbon number 2, 5 carbons long, alkane. Now, the other way to name this is using mono. Since there's just one methyl group, you can also name this 2-mono-methylpentane. But normally we don't use the mono. It's totally optional. You may use it if you like, because if we had 2 methyl groups, let's say we had another one, like right here, we would say 2,3 dimethyl pentane. So whenever there's a di or tri, you have to have 2 numbers. If it's tri, you have to have 3 numbers. Tetra, 4 numbers. If you had mono, that would mean you'd have 1 number. So but remember, mono's implied here. Okay. So that's the first example.
I have a question about this one actually.
Yeah, good.
If there isn't that other methyl, so it's still the 2-methylpentane.
Yeah.
If you go back to the left, I guess, so we can see the whole molecule, is it possible to, because we count, I see how you numbered the carbons here. Would it be wrong to number the top right one as the first and do kind of a horseshoe all the way up and left?
Good
Is that
question.
different?
It's perfectly fine because each one has 5. So let's temporarily get rid of this. So if we started here, okay, so our pen didn't leave except for this one here, right?
Right, yeah.
And if you name this, it'd be the same name because we have 1, 2, 3, 4, 5. And they going the other way, it's 1, 2, 3, 4, 5. And in the pink version, we have this would be end up the branch right here. That's coming off of carbon number 2. So the answer is exactly the same.
Okay, cool.
So and again, the trick is figuring your backbone. Is your pen or marker going to leave the paper to get onto that other carbon you missed? If the answer is yes, then you have branching. If you're able to cover all the carbons without lifting your pen, then it's all part of the backbone. Now, your book does not in fact, no books describe that getting the backbone using a marker and lifting it off the paper, except for me. And this was invented by a student of mine about 12 years ago. And I've been using markers, colored markers ever since. She was a wonderful student. She had 3 kids, single mom, worked part-time, and got a very high A in my class. I don't know when she slept. She did a couple things. She took 3 classes from me, and depending on whether it was organic or inorganic, but the organic side of it, she came up with this. And I've been using it ever since. I really think it's clear because if you don't color things, you lose sight of what was the backbone again. If you use the highlighter, you know exactly what the backbone was because it's in yellow or whatever color you choose your backbone. So did I answer your question okay?
Yeah, perfectly. Thanks.
Okay, so this is the line version. Okay, 1, 2, 3, 4. 4 carbons long. And we have a carbon off the backbone that we had to lift our pen to cover. Okay, so let's name this guy here. Okay, so remember it's in 3 parts now. 2 parts if there's no branching, and there's definitely branching. So the backbone has got 4 carbons in it. So that's going to be a buta. And it's an alkane. So it's going to be ANE. And we've got 2 numbering systems. The top one has got the branch at carbon number 2. The bottom one's carbon number 3. So we're going to use the top number. So that's at branch 2. So it's 2, 1 carbon long, 2-methyl butane. I need to go to my Dell. I'm going to stop this for a second. See if I can turn off this stupid. See if that fixed it. Okay, so Katrin, did that answer your question, by the way? On Okay, good. Okay, so let's go ahead and jump back in.
Professor,
Yeah,
I had a question about the one we just did. Like for this one, since they're not labeled and we're just seeing a line drawing, is it methyl because there's only one C or one carbon?
yeah, exactly.
Okay,
Now we're
thank
going
you.
to do one with 2 carbons in a second. So if it's 1 carbon, it's a methyl branch. If 2 carbon, it's an ethyl branch. If it's 3 carbons, it's propyl. And that's all on these charts here. 1 carbon, methyl, 2 carbons, ethyl, 3 carbons, propyl. And in my class, I'd like you to say N-propyl if it's a straight series. If it's not coming off of the end carbon, it's going to be isopropyl. Okay, so let's go back to here. So let's start from scratch here now. Okay, so and then let's do one more thing. So let's see where I screw up. Okay, so let's get rid of the numbering too. Okay, so we got this guy. We need to figure out backbone. So let's just start on the right. Okay, I didn't get all the carbons because I have to lift my pen to go over here to pick up those other 2 carbons. So that's one version of the backbone. Another version of the backbone, which is totally legal, could be like this. Because we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So either way, we get 6 carbons. And there's one more as well. That's right here. And that we have 1, 2, 3, 4, 5. So that one's invalid because it's shorter than the other 2. So we're going to use either yellow or pink. So let's use the yellow one. Okay, now we need to number the yellow. Now, since the branch comes off the left side, let's start counting on the left. Okay, now let's count from the right. So we notice the branches on carbon 3 or carbon 4. Carbon 3 red, blue 4. Red is lower, so we're going to get rid of the blue numbering. Does everyone see why we're using the red and not the blue? Three versus 4. Notice the hard math. This is pre-calc math in this class. Okay, so we're going to get rid of the blue ones, since those give us a higher branch number. Okay, so our branch is on carbon 3. And how long is it? Well, we've got the end is a carbon and a kink's a carbon, so it's 2 carbons. 2 carbons is ethyl. Okay, so we've got 3 parts again. Backbone is 6 carbons long, so that's hexa. And then it's an alkane, so it's A and E, hexane. And we have a branch on carbon number 3, so it's going to be 3 ethyl hexane. So this is backbone, and this is branch. So does this make sense? Okay, so let's make this a little more complex. Let's put another branch in this guy. Let's put a methyl group right there. Okay, So now we have two branches. Okay, so we have a methyl branch and an ethyl branch. Okay, the methyl is at carbon number 4. So the question is, which comes first? Ethyl or methyl? Alphabetically, which comes first? E or M? E comes first. So we're going to put the ethyl first. So it's 3-ethyl, 4-methyl hexane. Does that make sense?
So it goes by alphabetical rather than the number, since I
Yeah.
feel like intuitively it would be methyl than ethyl normally.
Because it's smaller?
Yeah, I guess so.
Yeah.
Just different ways of grouping them.
Yeah. This is just IUPAC though. There's it gets naming if you ever have a prescription drugs come with that paper in like 3-point font, and they name the drug using IUPAC. And that sucker is like 5 or 6 lines long. It is so complex. And so because of that, the IUPAC has very definitive rules for naming these. And one of them is when you have multiple branching, it's alphabetical. There's one exception to that, that's iso. Like if it was isopropyl or isobutyl, the I is not dropped. So instead of isopropyl, for example, this would be an I, not a P. That's the only one. Otherwise, it's this letter there. Okay, so let's see. So this is almost, this is very similar. Okay, let's see, let's start from scratch on this. Okay, so we need to mark all this out here. Okay, so what do we got here? It's already numbered for you, but if it wasn't numbered, I mean, it's sort of obvious which is the longest backbone. Numbering is going to be questionable though. Okay, so that's the longest backbone, 7 carbons long. Now we've got 3 branches, 2 methyls, and this is what an isopropyl looks like. An isopropyl joins in the middle carbon. Okay, If this was just 3 carbons straight, it would be N-propyl. So this isopropyl, meaning it joins in the middle. N-propyl means it joins on one of the ends. So this is a middle join. This is an end join. So this is 3 carbons long, so it's a propyl branch. Joins in the middle, so it's an isopropyl. Okay, all right. So we've got numbering wise. Okay, so we've got a branch at 2, 3, 4. If we name this starting on the right, the branch would be 4, 4 is the same, but the blue numbering gives us really high numbers for the 2 methyl groups. So we're going to be using the black numbers like they did for us. Okay, does everyone see why the black gives us lower numbers as opposed to the blue? And you're going to have to be doing this alternate naming each time you name a molecule until you can, after a while, you can kind of see that most of the branching is on the left. So that means if we start numbering on the left, the numbers will be lower. Okay, so we've got these are both methyl branches. This is an isopropyl branch because it attaches in the middle. Now this would be what a N-propyl branch would look like. So it attaches on the end. Okay, so let's name this now. Okay, so the backbone is 7 carbons long. So that's going to be so backbone is 7 carbons long. That's a hepta. And we've got a number of branches. And we've got methyls at carbons 2 and 3 and isopropyl. Now remember I said the isopropyl is not a P, it's an I. So that means the isopropyl is going to be named first. So it's going to be 4 isopropyl. Okay, then we've got 2 methyls at carbons 2 and 3. So it's going to be 4 isopropyl, 2,3-dimethyl heptane. Okay. You guys okay with this? Now this requires lots of practice. And I've given you lots of practice with Dry Lab 1. And don't forget, Monday is a holiday. So the Monday Dry Lab group, you need to do at home. And you can come in Wednesday's lab as well if you'd like. But if you can't make Wednesday, then go ahead and just do it at home. And also, Wednesday folks, think about a lab partner as well. And then get your drawer assigned today or next week. Okay, so any questions about this so far?
I have one question.
Yeah,
Because it's 2 and 3, the di is that what makes it the dimethyl?
exactly.
Okay. And then
And for-
also for the ISO versus the N, I know the ISO is an exception, so that'll be in front of anything. Is the N also an exception? Like, do we also put it first instead of going by alphabetical?
okay, the N is not gonna, that's a good question. Okay, the only thing that the di, tri, whatever, those don't count in alphabetizing, only the main M counts, except for ISO. There, the I counts as an I, not as a P. So was that your question?
That does clarify some stuff, but I just wanted to know more about like you said the ISO is an exception, but is N propyl also an exception?
Well, the N is like a 2,3.
Okay,
Actually, it's like not like a 2,3. It's like a di.
a di. Okay, that's what I just wanted to know.
So the N
Thank you.
propyl can be a P.
Okay.
Now, for all of you that are um, like systems, this is a very systematic approach to naming. What's nice about it is our next chapter is named exactly the same way. Chapter after that is named the same way, etc. So it's nice to get this system down now because you're going to be using it for the rest of the semester, except for biochem. Biochem's another story. But for the organic side of things, we're going to be using this. Okay, so one of the things that I mentioned earlier is if you have a cycloalkane. Now, alkanes, cyclic alkanes, uh, don't have thinks I'm drawing a circle. I'm not. They don't do that because they're cyclic. So they are rigid. It's the only non-spinning alkane are cyclic ones. Okay, so that rigidity is very important. Make a red flag there. Whenever you have rigidity, you can have isotopes. Now, when we get into, we're going to get into something called cis-trans isotopes. You've heard of trans because it's a big thing with fatty acids. You want no trans fatty acids. You only want cis. Trans are not natural, and hence they screw up your membranes. Anyway, so if it's rigid, check for isomers. Now, with cyclic alkanes, because they're rigid, we're going to have to check for isomers. And those are non-hydrogen branches. Okay, of the 4 forms of cyclic, and there's another one which is 7-sided. The 6-sided one is the most stable. That's because all the bond angles are 109.5 degrees. Every other cyclic structure, the bond angle is not that. That's why they're less stable. The most rigid and the most unstable of all the cyclic ones is this guy here. The cyclopropyl group. Very unstable. Okay. However, when you have a cyclic group, that one that automatically defines So whenever you have anything cyclic, it automatically defines the backbone. You don't have to do any counting. You got to do you count clockwise and counterclockwise to figure out the numbering, but as far as identification of the backbone, cyclic, boom, that's it. Okay, so all we're doing is we're adding a cyclo prefix in front of the backbone. Okay, so here we've got a cyclic backbone, hence it's automatically the backbone. And we have two branches, an ethyl and a methyl branch. So what we need to do is figure the numbering. So just start numbering at one of the branches, doesn't matter which one. And you're gonna number counterclockwise and clockwise, and just see how the numbering comes out. So if we start at number one for the ethyl group, if we count, we go number one, that means ethyls 1 and 1. However, the methyl group, the methyl branch, is going to be either at carbon number 3 or carbon 4. So the 1,3 is smaller than the 1,4. So that means counting wise, we're going to be counting clockwise. Does everyone see why the 1,3 is better than the 1,4 in terms of being smaller? All we're doing is adding up the branch numbers. And whatever that sum is smaller, that's when the group we're going to be using. Also, the numbering starts with the first group of the alphabet alphabetically. So ethyl is lower than methyl, so we start counting on the ethyl word. So here we have 1-ethyl, 3-methyl cyclopentane. Notice there are dashes on here. Separate things with a dash. It makes it really simple. Okay, so I mentioned if it's rigid, look for isomers. So there's geometric isomers and stereoisomers. The main thing is it's an isomer. And because we don't have free rotation, the location of the branching is going to be fixed. Okay, so here we have 1, 2, 3, 4, 5. So that's cyclopentane. And we have two branches. Okay, so if we start numbering here, the branches occur on carbons number 1 and 2. However, they're different. Notice that with cis, they both go down. They're on the same side. With trans, they're opposite sides. Which do you think is more stable, cis or trans? Well, that's a steric hindrance question. Which is more sterically hindered, cis or trans? Okay? Because these are as far apart as possible, when these two are sitting next to one another, this is the least stable because of steric hindrance. Because the methyl groups are real close together. Nature doesn't like that. So we're going to separate the methyl groups as far as possible. So between the two of these, the structure is almost the same. The formula is the same, except one is more stable than the other, and that's the trans. Okay. Physical properties. Um, did you cover in 305 intermolecular forces? Anyone remember?
Yeah, we didn't focus super heavily on it, but yes, at least for me.
Okay. In this class, we're going to talk about it a lot. They're called IMFs. So whenever you have strong IMFs, then you have high surface tension, high boiling point, high melting point. That's because they want to stick together. They want to stick together. It's going to be harder to boil it, harder to melt it. Also, there's something called surface tension, which makes the surface of the water sticky. So the IMF is directly proportional to boiling point, melting point, and surface tension. So high IMF means high polarity. Now, this is determined by looking at the periodic table. Over here is fluorine, oxygen, nitrogen, carbon. Hydrogen is over here. Down here is this point here on the periodic table. So this is F is the most ionic, the most high IMF. This is the least. So the closer you are to fluorine, the more polar your bond is going to be. So if we had a bond like this versus that, the HF bond is going to be more polar than the OH bond here, because this is the most polar molecule in the whole periodic table, highest IMF. So that means HF is going to boil higher than the OH bond here. So that's boiling point, melting point, and surface tension. So if we look at these guys. These are all the intermolecular forces. Sometimes ionic is included, sometimes it's not. I include it because it's very important because ionic things tend to have extremely high IMFs. Okay, we have ionic hydrogen bonding, dipole, dipole, London dispersion forces, and so higher in this, stronger the IMF or polarity. Hydrogen bonding is when H bonds to NOF. Whenever you have that, that's stronger than any other dipole-dipole. So we're going to look at, there's another concept here. You've probably already heard of this, but if you haven't, like attracts like. And that comes down to dissolve. So like dissolves like. And that's because of the intermolecular forces. So let's take oil, for example. Oil is very low IMF-wise. So it would dissolve other oils. It would dissolve things like it. Let's look at water. Water has hydrogen bonding in it, so it's very polar. So that's why water does not dissolve oil. Water is very polar. Oil is very nonpolar. Hence, they don't dissolve each other. So to remove grease, when you're washing dishes, you want to remove the grease from your pots and pans. Water doesn't do it. What do you have to add to your water to make it dissolve the grease?
Soap.
Soap. That's right. And that's because soap dissolves the grease because it attaches the water and grease together. It's like glue. Soap is something called an emulsifier. Emulsifiers have a polar and a nonpolar part. Now, in this class, I'm going to be asking, I'll give you a molecule, and I'll ask you, could this act as an emulsifier? So you're going to go through and identify all the functional groups and say that's a polar functional group, that's a nonpolar one. And you can determine whether will act as an emulsifier. If it has both of them in the molecule, it will be an emulsifier. Soap comes from fat. What happens is you saponify the fat. We're going to get into this in extreme detail. Also going to have a lab on it. We're going to make soap in here. So anyway, now we're going to be talking about intermolecular forces every single time I lecture from now on. So you're going to get to be comfortable with this after a while. And hopefully, I don't know what depth you went into in 305, but this is an introduction to it. Okay, are there any questions about that? Okay, so let's go back to your. So this is what soap looks like. We've got this non-polar part, and the polar part is the acid part. So this would make a good soap or emulsifier. Okay. So nonpolar molecules have weak intermolecular forces. Just nonpolar, low IMF. As we get bigger molecules, two things happen. The melting points go up and the boiling points go up. So MP and BP usually act together. One goes up, the other follows along with it because it's the same physical stuff going on in each of them that make it go up. So if we look at a table of alkanes now, starting from 1 carbon up to 10. You can see that the melting point gradually get lower and lower and lower. Boiling points, excuse me, let me back up. As the molecule gets bigger, the melting point gets higher because it's a negative number here. Boiling points go up. That's because it takes more energy to get the big molecule out of the liquid to the gas phase than the smaller one. Also, bigger molecules have more intermolecular forces, hence higher boiling point. So we're going to see a lot of these graphs like this. So we've got boiling point going this way, number of carbons going this way. And you're going to find that the alkanes and the alkenes have the lowest IMFs. They're going to go to ethers, alcohols, acids, hemiacetal aldehydes, a lot of stuff. But as far as intermolecular forces go, alkanes are the lowest. So anything above an alkane is not going to dissolve something under it because one's polar, one's not polar. Now, biochemistry-wise, that's a really important distinction because our body is basically a big sack of water with reactions going on all the time. And our body uses non-polar membranes to separate the chemical reactions from one another. So if you've got good membrane health by not eating trans fats, your membranes act more efficiently. So you start throwing trans fats into your membranes are made up of fats, then you have poor membranes. They're not very, they don't retain their integrity. Okay, I think what I'm going to do is, there's only two reactions for this alkanes. One is combustion. Basically, we burn things, and the other is we're going to add halogens to it. And I'm going to cover these when I cover the reactions under alkenes, because there are a lot of alkene reactions, only 2 reactions for alkanes. So I'm going to end that here. It's a lot, huh? Now, this is a typical amount of material for each functional group you're going to run into. In fact, this is probably the smallest because it has the smallest number of reactions. Now, we're going to see the next time we meet, which is going to be Wednesday, we're going to talk about alkenes. Alkenes have probably 7 or 8 reactions. Alkanes have 2. Alcohols have 7 or 8 also. So we're going to end up having to know about 20 different reactions for this unit. And I'll show you what a reaction is first thing on Wednesday. Okay, so for this, what we've done so far, I want you to concentrate on naming. Because every test is going to have 3 parts: naming, reactions, and intermolecular forces. Every single test, including the first one. So naming is important. It's also easier than reactions. Most students think the reactions are the hard part of this class, just FYI. And there's one person who had 309. That was is it Zanina Covington? Is she on? And 309 class has both 305 and 306 in it. So it's kind of an abbreviated 305 and abbreviated 306. Most of the emphasis in 309 is on the 306 side of things. Okay, so any questions at all about this so far? This is why I wanted you to download the slides, print them, so you can take notes on them. And if you've reviewed one of these lectures before you came today, this would be easier. So I want you to try to do that for the next alkene chapter. So download the slides, print them, watch an alkene video, take notes. Then on Wednesday, we can refine your parts where you had difficulty. Okay, so how are we doing? So Brenda, yes, this is more sterically hindered. You're absolutely right. Was that a question? Okay, are there any last minute questions?
I had a question. So just to clarify, I'm a little bit confused. So with our lab meeting today, is it optional or are we required to go?
Dry labs are optional. Doing the lab is not optional, but the reason I say optional is you can do it at home. Or you can come to class and some people drive like 2 hours to get here, though. That's why I leave dry labs as optional. In lab, you can do them at home. So does that make sense?
Yes, thank you.
Okay. Now also be thinking about a lab partner. Most of the time you'll be working in groups of 2, sometimes 4, depends. Like your first lab is on alcohols, and you're going to be working in groups of 2. The next one on steam distillation, you can be working in groups of 4. Yes, you need to buy a lab manual for this class. That's where all the labs are located. Okay, so it doesn't look like there are any questions. So let's go ahead and end this.